Humphry Davy begins his scientific journey at a time when chemistry was still struggling to become a modern science. Many substances had not yet been properly identified. The nature of chemical elements remained uncertain, and electricity was only beginning to reveal its extraordinary connection with matter. Into this changing world came a young man whose curiosity was almost impossible to contain. He would become one of the most celebrated chemists of his generation. He would isolate new elements, transform the study of electrochemistry, invent a revolutionary safety lamp for miners, and become a scientific celebrity in London. But perhaps his greatest achievement was something deeper. He helped demonstrate that matter itself could be broken apart and understood through the controlled power of electricity. Humphry Davy was born in 1778 in Penzance, Cornwall, in southwestern England. His childhood environment was far removed from the great scientific institutions of London. Cornwall was a region shaped by mining, rugged landscapes, and the extraction of metals from the earth. This environment would eventually influence his scientific imagination. As a boy, Davy was intensely curious. He read widely. He wrote poetry. He explored the countryside. He experimented with whatever materials were available to him. His education was not initially centered on advanced science, yet he possessed a quality that would become one of his defining characteristics. He wanted to understand things for himself. He did not simply accept explanations because an authority had given them. He wanted to know what happened when substances were mixed, heated, dissolved, or exposed to electricity. This curiosity became especially important during his teenage years. Davy became interested in chemistry at a time when the subject was undergoing a profound transformation. The older traditions of alchemy were gradually being replaced by quantitative experimentation. Scientists were beginning to weigh substances carefully, measure gases, analyze reactions, and search for consistent laws governing chemical change. One of the most influential figures in this transformation was Antoine Lavoisier. Lavoisier had helped establish the importance of precise measurement and had challenged older ideas about combustion and chemical composition. Davy encountered these new ideas and became fascinated by them. He began performing experiments himself. His early laboratory was far from sophisticated. He used relatively simple equipment and sometimes improvised apparatus from whatever materials he could obtain. But the lack of expensive equipment did not reduce his enthusiasm. If anything, it encouraged ingenuity. Davy's experiments eventually brought him to the attention of scientists in Bristol. In 1798, he joined the Pneumatic Institution, an experimental center devoted partly to investigating the medical and physiological effects of gases. The institution had been established by Thomas Beddoes, a physician and scientific thinker interested in the potential therapeutic uses of newly discovered gases. For Davy, this environment was transformative. He gained access to chemical equipment, scientific literature, and a community of researchers. More importantly, he gained the freedom to experiment. One of his earliest major areas of investigation involved gases. Chemists had discovered that different gases could have dramatically different effects on the human body. Some could support combustion. Others could extinguish flames. Some could be inhaled without obvious effects. Others produced powerful physiological changes. Davy became fascinated by nitrous oxide, commonly known as laughing gas. At the time, its effects were poorly understood. Davy began conducting systematic experiments on the gas, including experiments on himself. He inhaled increasingly large quantities and carefully recorded the resulting sensations. The effects were extraordinary. He experienced excitement, altered perception, laughter, and powerful changes in consciousness. Davy described these experiences in scientific detail. His work eventually led to the publication of a major study on nitrous oxide. The research was significant not simply because of the unusual experiences it documented. Davy demonstrated that gases could have complex effects on the human nervous system and that such effects could be investigated experimentally. He also suggested that nitrous oxide might have potential medical applications. At the time, however, its most important future use was not yet understood. The idea of using nitrous oxide as an anesthetic for surgery would develop later. Davy had opened a door without being able to see the entire room beyond it. His work with gases made him famous. In 1801, he was invited to London to become a lecturer at the Royal Institution. This was a major turning point. The Royal Institution had been established as a center for scientific education and experimentation. It aimed to bring scientific knowledge to a wider audience through lectures and demonstrations. Davy was exceptionally well suited to this mission. He was not merely a talented experimenter. He was a spectacular communicator. His lectures could attract enormous audiences. He performed dramatic demonstrations. He explained complicated chemical principles in language that ordinary people could understand. He made science exciting, at a time when scientific lectures were becoming fashionable among London's educated public. Davy became a genuine celebrity. People attended his presentations not only to learn chemistry, but to witness experiments that seemed almost magical. Bright flashes, explosions, strange gases, unusual chemical reactions, new substances. Davy understood the power of demonstration. A scientific principle could be remembered more easily when people had actually watched it happen. But beneath the spectacle was serious research. Davy's greatest scientific work was beginning. He became increasingly interested in the relationship between electricity and chemical substances. The discovery of the voltaic pile by Alessandro Volta had created a powerful new experimental tool. Unlike the static electricity machines used in earlier experiments, the voltaic pile could provide a continuous electric current. Scientists quickly realized that this current could produce remarkable chemical effects. Davy saw enormous possibilities. If electricity could cause chemical substances to separate, perhaps electricity could reveal the fundamental components of compounds that had previously seemed indivisible. He began conducting increasingly powerful electrochemical experiments. His equipment at the Royal Institution allowed him to work with much larger electrical currents than many earlier researchers had been able to produce. He applied electricity to molten and highly reactive substances. The results were extraordinary. In 1807, Davy investigated potash, a substance that had long been known but whose true composition remained uncertain. He passed an electric current through molten potash. At the negative electrode, a new metallic substance appeared. It reacted violently with water. Davy had isolated potassium. This was a historic moment. Potassium was not merely a new substance. Its discovery demonstrated that a material long treated as a simple chemical substance could be decomposed into more fundamental components through electrolysis. Davy continued. He turned his attention to soda or sodium compounds. Again, electrolysis produced a previously unknown metal, sodium. The implications were profound. Electricity was becoming a tool for discovering the hidden architecture of matter. Davy's experiments did not stop there. He investigated alkaline earth compounds and successfully isolated other elements, including calcium, magnesium, strontium, and barium. Some of these metals were extremely reactive and difficult to obtain through traditional chemical methods. Electricity made their isolation possible. With every new discovery, Davy strengthened a revolutionary idea. Chemical compounds were not necessarily fundamental substances. They could contain elements that behaved very differently from the compounds in which they were found. This helped reshape the concept of the chemical element itself. Davy's work also challenged older theories about chemical bonding and the forces holding substances together. Electricity was revealing that chemical affinity and electrical forces were deeply connected. The laboratory was becoming a place where invisible forces could be made visible through controlled experiments. And Davy was becoming one of the most important chemists in Europe. But his scientific career was about to take another remarkable turn. Because while he was uncovering new elements in the laboratory, a dangerous problem was threatening the lives of thousands of workers underground. Coal mines were becoming increasingly important to Britain's industrial economy. Deep beneath the earth, Miners worked in darkness, surrounded by combustible gases. One particular gas was especially dangerous: methane. When methane accumulated in underground tunnels, a single flame could ignite it. Explosions could tear through mines with devastating force. Miners needed lamps to see, but ordinary flames could also kill them. The problem seemed almost impossible. How could miners carry a light into a mine filled with explosive gas without creating an explosion? Humphry Davy would soon attempt to solve it, and the solution would require him to apply chemistry, physics, and practical engineering to one of the most dangerous environments imaginable. The problem facing Britain's coal miners was not simply a scientific puzzle. It was a matter of life and death. Coal mining had become increasingly important to Britain's rapidly industrializing economy. Coal-powered factories, heated homes, fueled transportation, and helped drive the expanding machinery of the Industrial Revolution. But obtaining coal came at an enormous human cost. As mines became deeper, workers encountered dangerous gases trapped underground. One of the most feared was methane, commonly called fire damp. Methane itself is invisible. It has no obvious warning that it is present. But when mixed with air in the right proportions, it can become explosively dangerous. The traditional method of lighting underground tunnels involved open flames. Miners needed light to work, yet the very light that allowed them to see could ignite the gas surrounding them. The result was catastrophic. Explosions could destroy tunnels, kill workers, collapse underground structures, and spread fire through entire sections of a mine. Mine owners and engineers desperately wanted a safer lamp. Several inventors had already attempted solutions. The challenge was deceptively simple. A lamp needed to produce enough light for a miner to work, but somehow prevent the flame from igniting the methane outside the lamp. The problem required understanding how flames behaved. Humphry Davy approached it as a scientist. He began investigating the conditions under which flames could pass through narrow openings. He discovered something crucial. A flame could not easily pass through sufficiently fine metal mesh because the metal absorbed heat from the flame and cooled the gases passing through it. This observation provided the foundation for his safety lamp. Davy designed a lamp in which the flame was surrounded by a cylinder of fine wire gauze. The lamp could still burn. Light could escape. Air could enter. But the gauze prevented the internal flame from reaching the explosive mixture outside under normal conditions. The principle was simple. Its consequences were enormous. The Davy lamp was introduced in 1815. It quickly became one of the most important safety technologies in the history of mining. The invention demonstrated something fundamental about Davy's scientific method. He did not solve the problem by guessing at a mechanical design. He investigated the underlying physical process. Why does a flame spread? What happens when heat is removed? How narrow can an opening become before combustion can pass through it? Once those questions were answered, an engineering solution became possible. The lamp also revealed the practical power of basic science. A phenomenon that might appear trivial in a laboratory could become a matter of survival underground. The safety lamp was not perfect. Methane could still be dangerous, and the lamp required careful use. But it dramatically improved miners' ability to work in hazardous environments and became an important symbol of applied scientific knowledge. Davy received enormous recognition for the invention. He was knighted in 1818, becoming Sir Humphry Davy. But the safety lamp also became the subject of controversy. Another inventor, George Stephenson, had independently developed a safety lamp around the same period. The question of priority created disagreement. Both men had contributed important ideas, and the controversy continued for years. Davy himself was not indifferent to recognition. He was ambitious. He enjoyed fame. He valued his reputation. This side of his personality sometimes contrasted with the image of the purely selfless scientist. Davy wanted to be remembered. He wanted his discoveries recognized. And yet, despite these human ambitions, his scientific contributions were enormous. His work in electrochemistry continued to expand. The discoveries of potassium and sodium had demonstrated the power of electrolysis, but Davy wanted to understand the broader principles behind chemical combination. He increasingly viewed electricity as a fundamental force involved in chemical attraction. The experiments of Davy and other researchers were helping establish electrochemistry as a major field of science. His work also influenced the development of atomic theory. John Dalton was developing the idea that matter consisted of atoms with different masses and that chemical compounds formed from atoms in definite proportions. Davy did not accept every aspect of Dalton's ideas immediately. Scientific theories were still developing. The early 19th century was a period when chemists were trying to determine what exactly constituted an element, a compound, an atom, and a molecule. Davy's experiments provided crucial evidence. By isolating new elements from compounds, he showed that chemical substances could have hidden components with dramatically different properties. Potassium, for example, was a soft and extremely reactive metal. Yet compounds containing potassium could behave completely differently. Sodium behaved similarly. The chemical identity of a compound could not be understood simply by observing its overall properties. The components mattered. This was helping chemistry move toward a deeper understanding of matter. Davy's scientific reputation grew rapidly. He became one of Britain's most celebrated intellectual figures. The Royal Institution was packed when he lectured. His demonstrations attracted members of aristocratic society, politicians, writers, artists, and ordinary educated Londoners. Science had become a form of public entertainment. But Davy was more than an entertainer. He was capable of extraordinarily demanding experimental work. His electrochemical experiments required powerful batteries, careful control of temperatures, highly reactive substances, and painstaking observation. Some of the materials he handled were dangerous. Chemical burns, poisonous fumes, explosions, and electrical hazards were genuine possibilities. Laboratory safety standards were primitive compared with those of today. Scientists often learned through experience just how dangerous a substance could be. Davy himself suffered injuries from experiments. One of the most famous incidents involved nitrogen trichloride. This substance was extremely unstable and could explode unexpectedly. Davy investigated it because he wanted to understand its chemical composition. The work was extraordinarily dangerous. An explosion caused serious injuries to his eyes. The incident was a warning of how easily scientific curiosity could cross into physical danger. Yet Davy continued working. His curiosity was stronger than his fear. This characteristic had both positive and negative consequences. It allowed him to investigate phenomena other scientists might avoid, but it also exposed him to unnecessary risks. Modern laboratory safety exists partly because scientists learned, often painfully, what can happen when experimentation outruns caution. Davy's scientific life also brought him into close contact with another young researcher who would eventually become one of the most important scientists of the 19th century. His name was Michael Faraday. Faraday came from a poor background and had received very little formal scientific education. He worked as a bookbinder's apprentice, but he read scientific books intensely and became fascinated with chemistry. In 1812, Faraday attended one of Davy's lectures at the Royal Institution. He took detailed notes. Those notes eventually reached Davy. Faraday's enthusiasm impressed him. In 1813, Davy hired Faraday as a laboratory assistant. The decision would have enormous consequences for the future of science. Faraday would become Davy's assistant, collaborator, and eventually one of his intellectual successors. At first, the relationship was productive. Davy recognized Faraday's extraordinary experimental ability. Faraday learned from Davy's techniques, lectures, and approach to scientific investigation. He gained access to equipment and experiments that would have been completely beyond his reach otherwise. Davy, meanwhile, gained a talented young assistant who could help with laboratory work. But their relationship would become increasingly complicated. Faraday's abilities were obvious. He was exceptionally careful. He possessed remarkable experimental intuition. He could observe subtle effects and design ingenious experiments. Over time, Faraday would begin developing ideas of his own. Eventually, the student would become one of the most important experimental scientists in history. But before that future unfolded, Davy's own scientific career was entering a new phase. His health began to suffer from years of intense work. His eyesight was damaged. His body had endured repeated exposure to hazardous substances. His enormous workload placed him under considerable strain. Still, he continued traveling, lecturing, experimenting, and writing. He also developed an interest in agriculture and chemistry. He studied soils and fertilizers and explored ways chemistry could improve agricultural productivity. His interests were remarkably broad. He did not see chemistry as a narrow academic subject. Chemistry was connected to mining. Mining was connected to industry. Industry was connected to energy. Agriculture was connected to food. Medicine was connected to gases and chemical substances. Everything seemed to lead back to the same fundamental question: what is matter made of, and how does it change? Davy's answer was increasingly shaped by electricity. The more he experimented, the more convinced he became that electrical forces played a central role in chemical combination. His work helped establish electrochemistry as a powerful method for studying matter. And yet, despite all his success, Davy's career was approaching a turning point. The young assistant who had once stood quietly beside him in the laboratory was beginning to emerge as a scientist in his own right. Michael Faraday's rise would eventually become inseparable from Davy's legacy, and their complicated relationship would reveal that scientific greatness is not only about making discoveries. It is also about recognizing talent, dealing with competition, and accepting that the people who learn from you may eventually travel further than you ever imagined. The relationship between Humphry Davy and Michael Faraday became one of the most interesting connections in the history of 19th century science. When Faraday first entered the Royal Institution, he was not a famous scientist. He was a young man from a modest background who had worked as a bookbinder and had educated himself largely through reading. Davy, by contrast, was already internationally famous. He had isolated new elements. He had transformed electrochemistry. He had invented the miner's safety lamp. He had become a celebrated lecturer. He was a fellow of the Royal Society and one of Britain's most prominent scientific figures. Faraday entered this world as an assistant, but Davy quickly recognized something unusual in him. Faraday possessed extraordinary experimental instincts. He could handle apparatus carefully. He noticed small details. He remembered observations. And perhaps most importantly, he was relentlessly curious. Davy gave him opportunities to work in the laboratory. Faraday learned by watching, then by assisting, then by experimenting. Eventually, he began producing observations of his own. For a time, Davy and Faraday worked productively together. Faraday accompanied Davy on a scientific tour of Europe, where they met some of the leading scientists of the period. The journey exposed Faraday to a much wider scientific world. He met major European researchers. He observed different experimental techniques. He encountered new theories, and he gained confidence. The experience was enormously important for his development. Yet the relationship between the two men was not always easy. Davy was proud and ambitious. He had become accustomed to being one of the most brilliant scientific figures in Britain. As Faraday's abilities became more apparent, tensions developed. Years later, Faraday would surpass his former mentor in scientific influence. But during these early years, Davy remained the dominant figure. Faraday's career was still only beginning. Meanwhile, Davy continued his own investigations. His work in chemistry had already demonstrated that electricity could separate compounds into their constituent elements. But he wanted to understand chemical forces at a deeper level. Why did substances combine? Why did some elements react violently while others remained stable? Why could electricity break certain compounds apart? These questions were part of a much larger transformation occurring in chemistry. Scientists were moving away from vague concepts of chemical affinity toward increasingly quantitative explanations. The concept of atoms was becoming more influential. John Dalton had proposed that different elements consisted of different kinds of atoms, each with characteristic weights. Chemical compounds could then be understood as combinations of atoms in definite proportions. Davy's experimental discoveries supported parts of this emerging framework, but he also challenged aspects of the established understanding. His work showed that substances previously regarded as fundamental could actually be compounds. This was particularly important in the case of the alkalis and alkaline earths. Potassium, sodium, calcium, magnesium, strontium, barium. These substances were now recognized as elements. Their isolation changed chemistry dramatically. The periodic table did not yet exist. Scientists did not yet possess a complete classification of the elements. But Davy's work was helping build the foundation from which later chemists would develop one. His experiments also contributed to a changing understanding of chlorine. At the time, chlorine was commonly thought to contain oxygen because of the prevailing chemical theories. Davy investigated the substance and argued that chlorine itself should be regarded as an element. This was a major challenge to established chemical thinking. Again, his approach was based on evidence. If chlorine could not be decomposed into simpler substances using the methods available, then perhaps it should be considered fundamental. The question of what constituted an element was becoming increasingly precise. Davy's work contributed to that clarification. His scientific reputation continued growing. He received numerous honors. He became president of the Royal Society in 1820. The position placed him at the center of British scientific life. Yet leadership brought new responsibilities. Davy was no longer simply an experimental chemist. He was now expected to represent British science, manage institutional relationships, support scientific research, and navigate the complicated social world surrounding elite scientific organizations. The transition was not always easy. Davy's personality could be intense. He could be charming and generous, but he could also be proud, competitive, and sensitive to criticism. His ambition had helped drive his scientific achievements, but ambition could also create tension. His relationship with Faraday became increasingly complicated. Faraday continued developing his own experiments. Eventually, he began investigating electricity and magnetism. This was the beginning of a transformation that would eventually revolutionize physics. Faraday discovered electromagnetic rotation and later developed fundamental ideas about electromagnetic induction. These discoveries would lead to the development of electric motors, generators, transformers, and much of the technology underlying modern electrical civilization. Davy could not have known how far his young assistant would eventually go, but his decision to give Faraday a place in the Royal Institution was one of the most consequential acts of mentorship in scientific history. Davy's own later work became increasingly concerned with chemistry, agriculture, and geological processes. He investigated ways to improve farming through chemical analysis. He studied the composition of soils. He examined the role of minerals in plant growth. He explored how chemistry could be applied to practical problems affecting food production. This was entirely consistent with his philosophy. Science should not remain isolated from everyday life. The same principles that explain chemical reactions in a laboratory could potentially improve agriculture, mining, manufacturing, and medicine. But Davy's health was deteriorating. Years of intense experimentation had taken a physical toll. He had suffered serious injuries. His eyesight had been damaged. He experienced periods of severe illness. His nervous system and general health were increasingly fragile. Yet he continued working. He traveled extensively. He visited Europe. He spent time in Italy and Switzerland. He continued observing nature and writing about scientific subjects. In his later years, he became increasingly interested in philosophical questions surrounding science. He reflected on discovery itself. What did it mean to understand nature? How much of reality could human beings actually comprehend? Were scientific laws descriptions of reality, or simply descriptions of how phenomena appear to us? These questions showed that Davy was not satisfied with merely collecting facts. He wanted to understand the deeper meaning of scientific knowledge. He also continued writing poetry and philosophical reflections. This combination of science and literature was characteristic of his personality. Davy did not see imagination as the enemy of science. He believed imagination could help scientists formulate possibilities. But those possibilities had to be tested. An idea was not valuable merely because it was beautiful. It became scientific knowledge only when evidence supported it. This distinction would become increasingly important as science matured. By the 1820s, Davy's health had become a serious concern. He eventually suffered a stroke. His ability to work declined. He retired from the presidency of the Royal Society in 1827. His later years were spent largely outside Britain. He continued to write and reflect on science, but his physical condition made sustained laboratory work increasingly difficult. Yet his influence was already secure. The elements he had isolated had become fundamental parts of chemistry. The safety lamp had transformed mining. His electrochemical experiments had helped establish a new field of science. His lectures had popularized chemistry among the British public, and his mentorship had helped launch the career of Michael Faraday. Davy's story, therefore, became larger than the individual discoveries he made. He had helped change the relationship between science and society. The scientist was no longer simply an isolated scholar. Science could be a public activity. It could educate ordinary people. It could solve industrial problems. It could protect workers. It could create new technologies. And it could reveal entirely new forms of matter. Davy had helped demonstrate all of this. But his final years would bring an important change in perspective. The young scientist who had once raced from experiment to experiment now found himself reflecting on mortality, the limits of knowledge, and the temporary nature of scientific fame. He had spent his life trying to uncover the hidden forces of nature. Now nature itself was reminding him of the limits of the human body. And as his health declined, the legacy he had created was beginning to move beyond him. By the final years of Humphry Davy's life, the world of science had changed dramatically from the one he had entered as a young man in Cornwall. Chemistry was becoming a modern experimental discipline. Electricity had become a powerful tool for investigating matter. New elements had been discovered. Industrial technology was advancing rapidly. Scientific institutions were growing in influence, and the public had developed an increasing fascination with scientific discovery. Davy had helped drive much of this transformation, but he would not live to see its full consequences. His health continued to deteriorate. Years of intense laboratory work, dangerous chemical exposures, exhausting travel, and repeated illness had taken their toll. He had already suffered serious injuries during experiments, including damage to his eyesight. He had also experienced a stroke. The man who had once spent hours surrounded by chemical apparatus now found sustained scientific work increasingly difficult. Yet his mind remained active. He continued writing. He continued observing. He continued thinking about science. His later reflections reveal a scientist who had become increasingly philosophical about the nature of discovery. Davy understood that scientific knowledge was never finished. Every answer created new questions. Every discovery revealed another layer of complexity. When he isolated potassium, he had not completed chemistry. He had opened new questions about the nature of elements. When he discovered sodium and the alkaline earth metals, he had not explained all chemical reactions. He had revealed how much remained unknown. When he investigated electricity, he did not uncover the ultimate nature of matter. He discovered new relationships between forces that scientists would spend generations trying to understand. This was the pattern of scientific progress. The frontier moved forward, but it never disappeared. Davy's career also demonstrated the importance of instruments. The voltaic pile had given scientists a new way to manipulate matter. Electricity was no longer merely a strange phenomenon observed through sparks and static charges. It had become a laboratory tool. By passing current through compounds, scientists could force chemical transformations that were impossible to achieve through ordinary methods. This opened an entirely new pathway into the structure of matter. The discoveries Davy made through electrolysis would eventually become part of the larger story of modern chemistry. Later scientists would organize elements into systematic classifications. The periodic table would emerge. Atomic theory would become increasingly sophisticated. The electron would be discovered. The structure of the atom would be investigated. Quantum mechanics would eventually transform the understanding of matter and energy. Davy could not have imagined these developments. Yet his experiments formed part of the chain that made them possible. His work helped establish the principle that electrical forces could reveal hidden chemical structures. This principle remains fundamental to modern science. His influence was also visible in the world of technology. The safety lamp he developed for miners represented an early example of scientific engineering directed toward occupational safety. It was not merely a clever device. It embodied a method. Understand the dangerous physical process. Identify the conditions that allow it to occur. Change those conditions through design. Reduce the risk. This way of thinking became increasingly important during the Industrial Revolution. Factories, mines, railways, and chemical industries created new dangers. Scientific knowledge could be used not only to increase production, but also to reduce human suffering. Davy's safety lamp became part of this broader transformation. Its impact reached far beyond the laboratory. Deep underground, miners could work with greater protection from explosive gases. The lamp became a symbol of the connection between scientific discovery and human survival. But Davy's greatest legacy may have been the way he communicated science. At the Royal Institution, he demonstrated that scientific knowledge could attract large public audiences. His lectures were carefully prepared performances. He knew when to explain. He knew when to demonstrate. He understood the power of visual evidence. A flash of electricity could communicate a principle more effectively than pages of abstract description. A chemical reaction could transform an invisible concept into something people could see. Science became an experience. This helped establish the Royal Institution as one of Britain's great centers of public scientific education. And Davy's influence did not stop with his own lectures. Michael Faraday eventually became one of the Royal Institution's greatest scientists and communicators. Faraday continued the tradition of bringing difficult scientific ideas to wider audiences. His Christmas lectures became famous. The institution became a place where generations of people could encounter science directly. In this sense, Davy's influence survived through an institution as much as through his discoveries. His relationship with Faraday is particularly important when considering his legacy. History often remembers Faraday as the greater scientific figure. Faraday's discoveries in electromagnetism transformed the modern world. He discovered electromagnetic induction. He developed the foundations of electric motor and generator technology. He introduced fundamental concepts in electromagnetic science. His work eventually influenced the electrical systems that power modern civilization. But Faraday's journey began inside Davy's laboratory. Davy gave him an opportunity. He recognized his ability. He allowed him to enter a scientific world that would otherwise have been extremely difficult for someone from Faraday's background to access. Their later relationship became complicated, and Davy could sometimes be protective of his own scientific reputation. But the mentorship remains historically significant. A scientist's legacy is not measured only by discoveries made personally. Sometimes it is also measured by the people whose careers they helped begin. Davy left behind a generation of scientific ideas, but he also helped cultivate a person who would transform physics. This is one of the quiet forms of influence in science. A discovery can be written into a textbook. A student can carry a teacher's influence into an entirely new field. Davy's own life, therefore, continued through Faraday's work. The connection between the two men is a reminder that science is not created by isolated geniuses working alone. It is passed from person to person. Ideas are inherited, questioned, modified, and expanded. One generation provides the tools for the next. Davy himself had learned from the scientists who came before him. He built upon the work of Lavoisier, Volta, and many others. Faraday built upon Davy. Later scientists built upon Faraday, and the process continued. In this way, scientific progress resembles a vast conversation across time. No single scientist speaks the final word. Davy's life also provides an important lesson about scientific risk. In his era, experimental chemistry could be extremely dangerous. Scientists worked with substances whose properties were poorly understood. They had limited protective equipment. There were few standardized safety procedures. Accidents were accepted as part of experimental life. Davy's injuries remind us how different the scientific workplace once was. Modern laboratories are built around principles of containment, protective equipment, ventilation, chemical labeling, risk assessment, and emergency procedures. These systems developed partly because generations of researchers discovered, sometimes painfully, what could go wrong. Davy's experiments therefore belong to both sides of scientific history. They demonstrate extraordinary courage and ingenuity. But they also remind us that scientific curiosity must be balanced with caution. The goal is not simply to perform an experiment. The goal is to perform it safely enough that knowledge can continue. As Davy's health declined, he spent increasing amounts of time traveling in Europe. He visited places where the landscape itself became a source of scientific reflection. Mountains, rivers, minerals, and geological formations offered evidence of the immense forces that shaped the planet. Even away from his laboratory, he continued observing. Science had become a way of seeing. A rock was not simply a rock. It was evidence. A mineral was not simply a mineral. It was a chemical system. A flame was not simply light. It was a process governed by physical and chemical laws. A mine was not simply a workplace. It was an environment where chemistry could become a matter of life and death. This way of looking at the world was perhaps Davy's deepest contribution. He trained himself to see hidden processes behind ordinary phenomena. He taught others to do the same. Humphry Davy died in Geneva in 1829 at the age of 50. His life had been relatively short, but its intellectual reach was extraordinary. In only 5 decades, he had transformed major areas of chemistry and scientific education. He had isolated several elements. He had advanced electrochemistry. He had investigated gases and their physiological effects. He had developed the miner's safety lamp. He had helped establish modern public scientific lectures. He had influenced agricultural chemistry, and he had helped launch Michael Faraday's scientific career. His name became permanently connected with some of the most important scientific developments of the early 19th century. Yet perhaps the most remarkable thing about Davy's career is the way his work connected pure science with practical human needs. His experiments with electricity helped reveal new elements. Those elements became part of modern chemistry. His investigation of flames led to a lamp that protected miners. His study of gases contributed to knowledge that would eventually influence anesthesia. His lectures helped make science part of public culture. His mentorship helped produce another scientist whose work would transform the technological world. The connections continued outward. One discovery led to another. One experiment opened another field. One student became another generation of scientific knowledge. Davy's story also reveals the unpredictable nature of discovery. He investigated nitrous oxide partly because he wanted to understand its effects. He could not have known that generations later, related knowledge would contribute to the development of surgical anesthesia. He investigated electrolysis to understand chemical decomposition. He could not have known that electrochemistry would eventually become essential to batteries, industrial chemistry, metal extraction, and countless technologies. He created a safety lamp to protect miners. He could not have predicted the enormous future of industrial safety engineering. This is often how science works. The importance of an experiment may not be visible when it is performed. A discovery can remain dormant until another generation finds a new application for it. That is why scientific curiosity matters, even when immediate practical benefits are not obvious. Davy's life was built around curiosity. He wanted to know what substances were made of. He wanted to know what electricity could do. He wanted to know how gases affected the body. He wanted to understand combustion. He wanted to understand chemical forces. He wanted to solve practical problems. And he was willing to experiment. His greatest strength was not that he knew everything. It was that he was willing to investigate what he did not know. That attitude remains at the heart of science. There is also a deeply human dimension to his story. Davy became famous. He received honors. He was celebrated by society. He moved among Britain's intellectual elite. But fame did not make him immune to failure, injury, illness, competition, or uncertainty. His relationship with Faraday became complicated. Some of his scientific ideas were later modified. His health deteriorated. His life ended relatively young. Yet the work survived. This is perhaps one of the most meaningful aspects of scientific legacy. The individual eventually disappears. The experiment remains. The measurement remains. The method remains. The discovery becomes part of knowledge that belongs to everyone. Today, when we encounter the elements potassium, sodium, calcium, magnesium, strontium, and barium in chemistry, we are living in a scientific world partly shaped by Davy's experiments. When we study electrochemistry, we encounter principles that developed through the kind of work he pioneered. When we examine the history of mine safety, his lamp represents an important step in protecting workers. When we visit the Royal Institution or encounter the tradition of public scientific lectures, we can see the influence of the world Davy helped create. And when we look at the career of Michael Faraday, we see perhaps the most remarkable continuation of his legacy. Humphry Davy did not solve every problem he encountered. He did not create modern chemistry by himself. He did not discover every element. He did not fully understand electricity. He did not live long enough to see the scientific revolutions that followed. But he pushed the boundaries of what was known. He showed that electricity could tear apart compounds and reveal hidden elements. He showed that careful study of combustion could save lives. He showed that scientific lectures could inspire an entire public. And he showed that a person from outside the traditional centers of intellectual power could rise through curiosity, experimentation, and determination. His life began in Cornwall, far from the laboratories and lecture halls where he would eventually become famous. He rose through a combination of talent, opportunity, relentless work, and a willingness to investigate questions others had not yet answered. His career was not perfect. His personality was not simple. His methods sometimes carried enormous risks. His relationships with colleagues could become difficult. But his scientific imagination was extraordinary. He looked at ordinary matter and suspected that something deeper was hidden beneath its surface. He looked at electricity and saw a tool for discovering the structure of matter. He looked at a dangerous flame underground and saw a problem that chemistry could solve. He looked at a young bookbinder's assistant named Michael Faraday and recognized a potential scientist. And perhaps that is the final lesson of Humphry Davy's life. Scientific progress begins with attention, with a willingness to look carefully at something everyone else has become accustomed to seeing. A flame, a mineral, a metal, a gas, a spark, a chemical reaction, a question. Davy looked closely. Then he experimented. And through those experiments, he helped reveal a world that had always been there, but had remained invisible to the human eye. The elements he isolated had existed long before he discovered them. The electrical forces he investigated had shaped matter long before humans understood electricity. The dangerous gases in mines had threatened workers long before his safety lamp. The principles of chemistry had always governed nature. Davy's achievement was to make some of those hidden principles visible. He gave humanity new tools for understanding matter. And once those tools existed, other scientists could take them further. That is how knowledge grows. One experiment, one observation, one question, one generation after another. Humphry Davy's life ended in 1829, but the scientific world he helped build was only beginning. The chemistry of the 19th century would continue developing. Faraday would transform electromagnetism. The atomic theory would mature. The periodic table would eventually organize the known elements. Modern physics would reveal deeper structures inside atoms. Electrochemistry would become essential to industry and technology. And the scientific method would continue moving toward a world Davy could scarcely have imagined. He did not see that future, but he helped make it possible. And that is why Humphry Davy remains more than a name attached to a list of chemical discoveries. He represents a particular kind of scientific mind, restless, experimental, imaginative, practical, and unwilling to accept that the unknown must remain unknown. He entered the laboratory with questions. He left behind new elements, new methods, new technologies, new institutions, and a scientific legacy that continued long after his final experiment. The young boy from Cornwall could not have known where his curiosity would take him, but he followed it. And sometimes that is where the greatest discoveries begin,